Quantum mechanics is often described as a weird and unintuitive theory impossible to understand. A theory that never gives precise values, but only probabilities to the possible outcomes. You might have heard that electrons don't have a precise position and momentum, but only probability distributions describing their movement. As for example, the all-knowing Wikipedia puts it, generally, quantum mechanics does not assign definite values. Instead, it makes predictions using probability distributions. Well, what does it really mean when we say quantum mechanics makes a prediction using a probability distribution? How come electrons don't have a precise position? And what is so unintuitive or weird about it? We observe probabilities around us in our everyday world all the time, even though the surrounding things are very much classical. This morning I checked the weather forecast. It said there is a 50% chance of rain. So is the weather a quantum mechanical phenomenon? For sure not. I was leaving from home and couldn't find my keys. So I didn't know their precise position. I could only state that they are more probably located in the hallway than in the fridge, for example. So are my keys quantum mechanical? Of course not. So how are these probabilities different from the ones of quantum mechanics? Is the difference between quantum mechanical and classical probabilities only a question of interpretation? The answer is naturally no. I doubt physicists would have spent longer than a century studying quantum mechanics if the difference was just semantic. Indeed, quantum mechanics is a much more intriguing theory than Wikipedia leads us to think. As one of the founding fathers of quantum mechanics, Niels Bohr, put it, those who are not shocked when they first come across quantum mechanics cannot possibly have understood it. The catch here is, the weirdness of quantum mechanics doesn't arise from the events being just more random than in classical mechanics. They might be no more random, but random in a completely different way. The rules that quantum mechanical probabilities follow are not the same as those of classical probabilities. So how do the quantum mechanical probabilities differ from the probabilities we are used to deal with? Perhaps the simplest example everybody knows of probabilities is a coin toss. So let's have a look. What would happen if we tossed a quantum coin? When tossing a coin, there is a 50-50 chance of getting heads or tails. If I decided to toss the coin twice, the probabilities would be unchanged. I could go on with the tossing, and the 50-50 chance of getting either outcome would retain. If now, instead of a normal coin, I had a quantum coin to toss, how would these probabilities change? Be it that a quantum coin is a completely imaginary object. In nature, coins never behave according to quantum mechanics. There are, however, some properties that can be thought as the coins of the quantum world. For example, electron spin can point up or down, just like a coin toss can give heads or tails. Now, if I had such a quantum coin and I would toss it, at the beginning I couldn't notice any difference with the classical coin. Half the time I would get heads and half the time tails, just like the normal coin. Now, if I could toss it again and again, half the time heads and half the time tails, I could keep on doing this and the probabilities would remain unchanged. So the outcome is exactly the same as for the classical coin. Are you somehow shocked? I doubt. And the weirdness? Well, in order to reveal this, we need to change the rules of our coin toss a little. I still toss the coin as before, but before the second toss, I'm not allowed to check which outcome the first toss gave me. If I was tossing just a normal coin, nothing would of course change, and the second toss would give heads half the time. But how about the quantum coin? Let's say before I toss the coin, my quantum coin is heads upward. After the first toss, just like for the normal coin, the probability of getting heads or tails is 50-50. But if I don't check the outcome and toss again for a quantum coin, the outcome is always tails. Always. Now is a good moment for being shocked. Nobel laureate Richard Feynman once wrote about quantum mechanics. The paradox is only a conflict between reality and your feeling of what reality ought to be. Indeed, behind the seemingly weird quantum probabilities underlies a set of rules which themselves are not particularly weird or in no way paradoxical. Even though those rules lead to results which seem odd against our everyday logic. We are so used to seeing the world the way classical physics explains it. Anything that can't be explained with it is shocking to us. That's why, for example, illusions are so entertaining. Now, what if we could develop a game in which the rules would be those of quantum mechanics? How would the world look like through the eyes of an atomic-sized person? How fast could you learn the rules and master the quantum game? And most importantly, after playing the game, would quantum mechanics no longer seem unintuitive to you?